Hello and welcome to my talk on the foundations of software testing here at the ISTA ECOOP Summer School 2021. My name is Marcel Böhme and I'm a senior lecturer here at Monash University and soon a faculty member at the Max Planck Institute for Security and Privacy in Bochum, Germany. So before I talk about software testing though, I just wanted to talk a little bit about my work. I try to achieve a lot of practical impact. So my work is in fuzzing, which is the automatic way of testing software. So we are trying to find security flaws in other programs. Simply said, I'm trying to make machines attack other machines. I'm actually concerned about three questions. So effectiveness is about finding all the bugs in the other machine. Efficiency is about finding as many bugs as possible, given the resources that I have, like only limited time. And scalability is, if I increase the resources that I have, how much more power would I have? For instance, if I, instead of having only one machine, I had 10 machines, I had 1 million machines, how much more bugs would I be able to find at the scalability? But more generally, I'm interested in foundations of software security. How can we provide assurances in software security? This includes software testing. And I'm particularly focusing on the fundamental limitations of those existing approaches. And I'm also trying to draw from several disciplines, including information theory or applied statistics. Okay, let's talk about software testing. The first thing you learn is that there's always input process output. So there's some process, and this process is what we want to test. This process often takes an input and produces an output. So testing is very simple. You want to test this process, and in our case, this is a program. So you write a test case, which is simply an input, and then you get the output being pass or fail, right? So test cases can pass or fail. That's all. That's software testing. Generate at least one failing test case for each bug in the program. This is our software testing problem. So today I want to answer a couple of questions. So suppose you have been writing test cases, maybe many of you have written test cases for your programs, and you haven't found any bugs. What does it tell you about the correctness of your program? No test case fails. Do you know whether your program is correct or not? Are there any bugs left? So you can't, right? So this is one question. Then can you make statements about the way you generate test cases? Is the manner in which you generate test cases effective? And then the next question is, how do you even measure effectiveness if there are no bugs, right? How do you know that your test generation technique really works if it doesn't find any bugs? So yeah, but there are also a couple of other simple questions that I want to answer. So how does your test case know something is a bug or a feature? Sometimes you might not even be able to tell what is a bug or a feature. What is the difference between effectiveness and efficiency? So often people get confused about these two ideas of effectiveness and efficiency. Then if we assume the most effective technique, something which can find all the bugs, right? When is this technique more efficient than just randomly generating test cases? It might be a weird question, but you'll understand what I mean with this later in the talk. And then many of you might join because you know about this idea, this approach called gearbox fuzzing, AFL, libfuzzer, and so on, has been really successful in the last 5 years. There are very large fuzzing platforms using gearbox fuzzers like AFL and libfuzzer. Why is it so successful? Why does it work so well? And lastly, a scalability question. How is a number of resources or available resources linked to the number of bugs that I can find? Okay, let's start at the beginning. A test case is simply a test input and a test oracle. So you execute an input on your program, and the test oracle tells whether the execution is expected or unexpected. Okay, that's the job of the test oracle. So you pass a test input to a program, and you see whether the output is expected. So here the oracle lives outside of the program at the end, essentially, but you can also have oracles within the program. And instead of asserting whether the output is expected, you assert whether a state is expected. So you can have unexpected intermediate states. So here in the bottom, you will see that there is a link to a talk that is being presented here at ISTA log-based slicing for system-level test cases. So I try to link some of those topics that I present here to talks. So if you are interested in any of those topics, you can just follow up and attend these talks. So here's an example of a test input and a test oracle output. So we give our program is some GIF tool, and we give it a file, which is the test input, and we see a crash. And obviously a crash is unexpected. So our test oracle output is some segmentation fault. Here in this case, it's a sanitizer called address sanitizer. But in some other cases, you don't want to test at the system level, right? Because you're developing a certain unit, you're developing a certain feature. You want to test that feature specifically. So you want to test that feature or that function in isolation. So you do unit testing. But the problem is the unit often doesn't live outside of the system. It cannot live because sometimes a global variable has to have a certain value, or memory has to be allocated, or it might access the internet and you don't have access to the internet, or it might need some data from a database, so you have to return some sample data. So what you do is you write a harness for this. So you wrap this unit into a test harness. And the approach is the same. You pass some input to check whether the output is expected or the behavior of this unit within the test harness is expected. So here's an example of the unit test. There are 3 unit tests here for the programming language called Scala. You have in the first test case, you have a list. You want to test the plus operator, and so you construct an empty list. You use the plus operator to append the string 1, and then you assert whether this resulting list is actually a list which contains the string 1. If it is not, then there's something wrong. The assertion fails, and it prints wrong list state. This is an example of a unit test. And the method call sequence is the input. So now the answer to the question that I raised earlier, how does the test case know if the test input exposes a bug, is the test oracle flags it as a bug. Very simple. We just delegate this problem of flagging things as a bug to the test oracle. So my question to you is, what kind of test oracles do you know? What kind of mechanisms do you know that can tell whether something is a bug or a feature? And as I said, you can type preferably into Discord, but you can also try to type into the chat. Eric says wrong termination. That's correct. If we know that's a wrong termination, like if it's a crash, definitely crash as an oracle. A predicate expressed in a programming language, yes. Can be like if a predicate is violated, like an assertion is violated. That's correct. It's one of the most simple ways of asserting correctness. Properties, testing properties of the output. Yes, you're always testing properties of the output, and human is also correct. Yes, human is also an oracle. So yes, as we have seen, assertion-based testing is one of the most well-known ways of asserting correctness. You have an assertion which simply says something is a bug or a feature. But you can generalize this a little bit. Instead of saying for specific input, this is the output that I expect, the concrete output that I expect, you can say, you can assert for all inputs that satisfy a certain precondition, that it should satisfy a certain postcondition. You assert correctness of the output for all inputs satisfying a certain precondition. And this is called property-based testing. Can we have a test oracle that tells for every input what is the expected output? So you have a program that produces some output for an input. Can you, for that program, always tell whether the output is expected for every input? So I'll give you an example. You want to implement this sign function, like sign of x. So do you know for all real numbers, without having another sign function available, right? So obviously the oracle for an implementation of the sign function is another sign function. But if you don't have this other function already, then we can't tell for all real values what the output of a sign function should be. So this is so in reality, if we don't already have an implementation of something, we might not always be able to say what is the expected output for an input. But there are certain kind of tricks that we can use. And here's a trick particularly for the sign function, but for many other things, which is called metamorphic testing. So we have certain mathematical laws, like the sign of pi minus x should always be equal to sine of x, right? So this is a mathematical law, and this has to hold for all real values of x. You just need to generate some random real numbers and check whether this property holds. Right? So this, even though we do not know for all inputs what the sine function does. And metamorphic testing is famous for its test of round trip properties. Often you have something where you need to do something and then undo something. So there's an inverse relationship. You have to compress something and decompress something, decrypt, encrypt, serialize, deserialize. So what you can then test is, without knowing encryption, if I take any input, encrypt this input, take the result and decrypt that result, I should arrive at the same input. This property has to hold, and that's called metamorphic testing. There's another trick, which is called equivalence modular input testing. For instance, if we do not know how a compiler works for every source code, right? Maybe we do not know what the compiler does for every source code. But what we could do is we can take a source code and add some unreachable code, right? We know that the output must be the same. The compiler must produce a binary that executes the same or produces the same result, because we are adding unreachable code. So we change something in the input and we expect the same output. Same thing with constraint solver. When we're testing constraint solver, we make the constraint unsatisfiable. We have an unsatisfiable constraint and we make it unsatisfiable again. If suddenly the constraint solver says it's satisfiable, then something is wrong, right? Regression testing is most well known. What we can do here is we just take the previous execution of a previous version of a program as the oracle for the next version of the program, right? So if a regression test case fails, something is wrong with either something is wrong with the test case or something is wrong with the program. In both cases, we get some important signal from the execution of a regression test suite. So here there are two talks about regression testing at ISTA. Another idea is majority voting. So you have a number of implementations of the same thing, like cryptographic protocols. If you have 10 cryptographic protocols and 9 out of these 10 say one thing and one says something else, then you want to have a closer look at that one thing, at that one implementation that says something else for the same input. This is called differential testing. Okay, so now we have these are so-called functional and semantic bugs, right? They're related to the behavior that you want to implement, but they're also bugs that are related to your operating system or bugs that are related to your programming language, like memory safety bugs that are not related to behavior, but related to the way your operating system works. So you can detect those bugs as well using so-called implicit oracles, buffer overflows, like crashes, exceptions, and so on. You can inject code sanitizers to detect memory errors and stuff like that, data races. Apart from these functional errors, you can also check non-functional errors, like if you're interested in performance or user ratings. Here at ISTA, we have talks on testing side channel, quantifying side channels, which is a non-functional property, or testing the accuracy or robustness of floating point arithmetic code, which is also a non-functional property. Okay, so software testing. Let's assume that we have the perfect test oracle. Let's get away. We have some other people who work on the test oracle problem. We assume that we have the test oracle problem. What's left for us is only to generate those inputs that then flagged by the test oracle as bugs. Generate at least one test input for each bug in the program. Okay, so now my question to you is, what are ways to generate test inputs? Yes, by hand. Mike, Eric, also by hand. Search-based approaches, that's correct. Symbol execution, fuzzing, bounded model checking, that's also correct. Good old random generation, absolutely. Using grammars, I'm also going to talk about grammars. So let's leave it at that. Manual test generation, as Mike and Eric said, absolutely. So what we do is we set up a concrete state. We just provide a concrete input and then assert a property of that state. And if that property is violated, then we see an error. But this is about a concrete state. That's the unit test that I showed earlier. But what we could also do is we could just, if we have a system that interacts with another system, we can record this interaction. Like you have a protocol implementation, you have a client talking to a server, and later you want to be the client as your test generator talking to your server, then you record a discussion between client and server and just replay that all the time and expect the same responses from the server. You can do the same for web testing or Android testing. You have an actual user click through your Android app and then you replay it. And whenever something changes in the output from your Android app, then something is wrong. So this is manually constructing test inputs. You can also automatically generate them. And we heard about symbolic execution, which falls under systematic testing. We heard about random testing. And we also heard about guided random, which I consider as the search-based approaches. So let me go through them one by one. So depending on how much information you have about the program, we consider black box, gray box, or white box. So if you do not have any program information, you just generate inputs at random, totally at random. It doesn't need to be uniformly at random, but through some random process. If instead you get some feedback from the program for the execution of a randomly generated input, then this is called a gray box approach, because your system is considered not as a black box, but as a gray box. You get some feedback. So this would be, for instance, search-based software testing, search-based approaches. So once you get the feedback, you can then essentially steer your test generation in a certain direction. And you do not need to be totally random, like you generate some bits, but you can also have generate structured inputs. Like if you have a file processing program, often there are some certain file formats. So if you generate inputs that are just totally random, the program will just discard it. But you can have structure-aware fuzzes, just randomly generate inputs from structures like grammars or file formats, just as well, right? So you can have this is called spatial structure, but you can also have temporal structure. Like in a protocol, certain things have to happen in a certain sequence. So you can specify this sequence using something like a protocol. And stepping back, this is the same as a grammar. So you can sample. You can essentially only generate valid inputs still at random. And the third approach is called white box test generation, where the system is considered as a white box. And test generation is actually a second order citizen. The first order citizen is the program analysis. Like symbolic execution, you first analyze the program, construct some path constraints, maybe along the paths that you want to execute, and then solve that constraint and generate the test case after the fact. So when we talk about software testing for the guided random approach or for the systematic approach, we consider software testing as either an optimization problem, where like search-based software testing, where we have to minimize a certain distance to a set of targets, or we want to maximize something like coverage. But we use approaches from optimization to make our fuzzer better for some definition of better. Or we consider software testing as a constraint satisfaction problem, like a symbolic execution. Okay, so now after generating a few test inputs, what does it mean if no bugs have been found? That was the question that we had in the very beginning. What does it mean if we do not find any bugs? Like we know how to detect bugs, right? We have the historical. We know how to generate test inputs. But what does it mean if we do not find any bugs after all of this? So here is Dijkstra very famously saying, program testing can be used to show the presence of bugs, but never to show their absence. So just a few words about Dijkstra. So back in 1969, he found a publication as a very long-winded process. So what he did is what we now consider like posting. So he would come up with these structured notes on structured programming and distribute them among his colleagues. So today, I think he would have probably been a very good blog post writer or tweeter. So this is a very good tweet, by the way. Okay, so what it means is we can't show, testing can only be shown, testing can only be used to show the presence of bugs, but never to show their absence. So now we've relaxed this a little bit. So instead of saying we can't say anything about the correctness of the program, we can at least about the probability that we still find bugs if we just continued the campaign for a little bit longer. The next question, is your test input generator effective? So now can we say anything about our test input generator? Particularly, how can we measure effectiveness if there are no bugs? And because this is a very abstract question, like we've heard about test generator and we've heard about these oracles, I want to make this a little bit more tangible for you. So here's a metaphor. So suppose you're hanging out with your friends at the lake and you're into fishing and you've been at the lake for 3 hours and never caught any fish. Now the question is, who is better at fishing? Who is the best at fishing? Right? You have not caught any fish. Who is the best? So how can you answer that question? So in testing, we have found several answers to that question. So one answer is we simply send all of our friends to representative lakes and participate in competitions, in fishing competitions. And for us, we essentially benchmark our fuzzers on other programs and then make conclusions about our own programs. Like if we are good at finding bugs in other programs, then we're probably also good at finding bugs in our programs. Here, the problem is if you do that just for all different kinds of representative programs, there might not be any bugs either, right? So we have a problem in resources. We only have limited resources. We can't benchmark. So the next idea then is, well, okay, we don't have the resources. Why not just focus on those programs that we know have bugs, right? Why don't we fish only at lakes that we know have catchable fish? So here the problem is a survivorship bias. We do not learn how good we are at catching fish that others don't know how to catch, right? We do not learn about a property of our fuzzer, how good it is at catching bugs that others don't know how to catch. Right? If you only have 1 hour and we know that in that lake there are only fish that can be caught within 1 hour, we do not learn how good we are at catching fish that others cannot catch in 1 hour. Right? And the second problem is we still need to create those bugs, those buggy programs somehow, and that's a resource problem as well. We have real bugs now. We have benchmarks like that now, like Magma and so on. The third idea is, well, if this is a resource problem and we don't have a lot of real bugs, maybe just use artificial bugs and take a lot of programs and inject artificial bugs in those. The problem is that those bugs might not be realistic, right? So our performance, how is our performance related when we catch artificial bugs? How is it indicative of our performance at catching real bugs? So then there's a lot of research about trying to catch more realistic kind of bugs, right? How injecting more realistic bugs. This is the current state of the art. Well, we still have that problem that there's the assumption that the best fuzzer for most programs is the best fuzzer for our program, but it might not be the case. So what can we do? So the most well-known way of doing this is coverage. So you can't find bugs in statements or parts of your program code that you do not exercise, right? That you do not cover. That's the hypothesis. So coverage-based evaluation is essentially measuring how good you are at covering, how good you are at finding bugs by the way you cover, by how much code you cover. So for programs, there are 3 kinds of coverage criteria: code coverage, input coverage, and requirements coverage. Code coverage is something like statement, branch, or diffuse pair coverage, or modified condition decision coverage. and they are stronger, some are weaker, and so on. But essentially, you cover elements, some elements in your code. Another idea is to look at how much of your input space you cover. Like if you have a structure like grammar or some kind of protocol, you can maximize coverage in this structure. There's also a lot of research. So previously there was a lot of research in combinatorial testing. Maybe there's also some research these days on combinatorial testing. But essentially, you have you assume that your program takes parameters as input, and you want to test all pairs of discrete parameters that your program takes as input. Like if you have a configuration and you want to test all pairs of configurations, or you test requirements. Like if you happen to have a specification, then you can also try to cover this specification. And this idea of artificial fish, of course, in benchmarking also comes here to testing how good you are finding bugs in your own program simply by seeding artificial faults into your own program. This is called mutation-based testing or fault-based testing. There's one talk here called Deep Crime, doing this for deep learning systems. Okay, so now the problem is not anymore to generate test input for each bug in a program, but for each coverage element, assuming that coverage is, of course, correlated with better bug finding. So then, am I saying, so I'm saying achieve 100% code coverage. That should be easy, right? And that's a question for the audience. What do you think? Achieving 100% code coverage, is that easy, possible? And the answer is, of course, because I'm asking this question, you can't cover 100%. But what do you think, why? Why can't we not cover 100% code? Yes, Apita, that's correct. That's absolutely correct, that code. Code that is simply not executable. There's some code that can just not be executed in your program. For instance, you have a test harness, right? For many unit test cases, you have a test harness. Some code can just not be reached through this test harness. Some code is not reachable at all for any inputs to that program. So here's a small graph demonstrating this. So when you generate test cases, usually there's a certain asymptote. So the more test cases you generate, you'll approach this asymptote closer and closer. So the problem is we do not even know how much coverage we can achieve. And let me explain why. So we do not know where this asymptote lives at all. Suppose we knew how whether a statement can be covered or not, then we could always encode our undesired behavior as a coverage problem, right? If unexpected behavior, cover this, right? Fail. If we could compute beforehand whether this can be covered, we wouldn't have to do any testing anyway, right? So the testing problem is as hard as the coverage problem. That's called a reachability problem. Right? We wouldn't need to do any testing if you could tell beforehand whether something could be reached. But what we can do, we cannot compute, but what we can do is during testing, we can at least estimate this asymptote. And this is some recent research in my group where we consider this as a sampling problem. Testing is a sampling problem, we sample test inputs, and we approach this asymptote. And so we use some estimation from ecological biostatistics to estimate this asymptote during input generation. There's still some problems, of course, but we're breaking ground. So, okay, so each is not possible. Generate at least test input for as many coverage elements as possible. That's now our problem. So then, am I saying that it should be better to systematically generate test inputs that cover most of the coverage elements rather than to randomly generate test inputs, right? And that's a question to the audience again. So I have a technique that systematically generates test inputs to cover most of those coverage elements. And compare that to a technique that just randomly generates test inputs. Which one is better? What do you think? And we can assume there's a correlation between code coverage and bug finding. We simply assume that. It's still fine. The answer will be the same. So we have two different answers. One is systematic is better. The other is random is better. A combination is better. That's always true. That's absolutely correct. What better means? Yes. Yeah, that's a critical part. What better means, but we definitely want to count the number of bugs found. But I haven't said all of what better means. A matter of speed, and speed is a very important word because it considers that factor that I'm going to come to. Program execution speed is not. It's also a factor. Okay, the answer is again wrong. Systematically generating test cases to achieve the most coverage might not outperform random testing. There are certain conditions when it does. And so here is a paper from 1990, right? So that's 30 years ago, more than 30 years ago. And here Hamlet and Taylor are talking about a paper published 1984, 1985 maybe, so even older than that. And so here, the last paragraph that I highlighted, Hamlet shows random testing to be superior to partition testing. So partition testing is simply trying to cover all the coverage elements. And its superiority increases with more coverage elements and with the program confidence required. And it sounds counterintuitive, right? And they have been struggling to resolve this problem for quite some time, through all of the 1980s and some of the 1990s. And then it just wasn't very interesting to look at this problem again. But here's as a result from our group, you have to consider the time. And so this is the difference between effectiveness and efficiency. You have to consider time. And I'm going to explain why, when random testing is better than a most effective technique by an example in a second. But there's a certain condition when both perform equally well and random testing performs better, and the effective technique performs better. So assume we have a program like this. We have a program called crash me that takes a string of length 4. And it crashes for the string bad exclamation mark. We have a couple of test input generation techniques. We start with the white box fuzzer. And what the white box fuzzer does, like a symbolic execution tool, it would generate one test input per path. And it's most effective. Why? Because for all criteria that we have just listed, it satisfies this criterion. It covers all the statements, all the branches, all the paths, and even reveals the bug, right? We have to enumerate one test input per path, and it will find the bug. And so there are 5 paths, and so it will discover the bug after about 5 inputs. Now we have a generational black box fuzzer. What it does simply is like a random test input generation technique. It all generates any arbitrarily chosen string of length 4. And we assume that in C, a character is 8-bit long, so it can take one of 256 values. So an expectation, it would take about 4 billion inputs for a random input generator to discover the bug, right? It's definitely not most expected because it's not guaranteed to find a bug. It's only a probability, right? So 4 billion inputs, there's a lot more than 5 inputs. But on my machine, it takes only 6.3 seconds. And we're going to shave off a little bit more time of this. But what we see here is that the white box fuzzer has to find the bug in under 6.3 seconds, right? So there is a time bound on the white box fuzzer, and there's specifically a time bound on for each input that it can generate before it finds the bug. It has to be faster than a certain time. So let's shave off more of these 6.3 seconds. and come up with other test input generation techniques. So here is a mutational black box fuzzer. Instead of generating inputs, we're mutating inputs. So what our mutational black box fuzzer does is it chooses a character in a string uniformly at random and substitutes it with any of the 256 characters. So starting from a seed called bad ? It would discover the bug after about 1,000 inputs. Well, a little bit cheeky, right? Because we are starting with a very good seed. So how do we get to that seed? And the answer is discover it. And that's the main contribution of gray box fuzzing. We're discovering these kind of seeds. So the key idea is very simple for gray box fuzzing. You add inputs that increase coverage. So suppose you start with any string of length 4. The next input that increases coverage starts with the letter B. And to generate that input, we would take about 1,000 inputs. Then we add that input to the seed corpus. On the left-hand side of this table, we see the seed corpus. We choose one of those seeds uniformly at random, choose one of the characters uniformly at random, and substitute it by one character uniformly at random. And after about 2,000 seeds, 2,000 input generations, you find the next coverage increasing seed, and so on and so on. So after starting from anything arbitrary to finding the bug, we only need 10K inputs. And on my machine, this takes about 150 milliseconds. So the white box fuzzer has to be really, really fast in order to beat the gray box fuzzer, which doesn't do anything else than randomly doing stuff and adding coverage increasing inputs. So one contribution in our paper that we published in 2016 was, instead of choosing seeds, in this case, uniformly at random, focus on those seeds that exercise low probability paths. So we can shave off even more time and find a bug in 4,000 inputs and after 55 milliseconds instead of 150 milliseconds. So key insight, if you're smart in testing, right, you get some better feedback. If your test input generation is not fast enough, and even a simple guided random test input generator will find more bugs in your limited time budget. Right, so time budget is important, and being fast enough in generating inputs is important. Okay, so next, the next and the last topic is, I'll just go very quickly because I think we are out of time, is scalability. So now let's take the most popular technique, which currently is square box fuzzing, and distribute it across a lot of machines. How does bug finding scale with the number of machines? That's the question that I'm asking, and I'm going to ask more specific question in a second. How does bug finding scale with the number of machines? So here's just to give you a little bit more, a very concrete setting. Google has been fuzzing a lot these days, and there's this project called OSS Fuzz, where they are fuzzing. This is old data. Currently, they're fuzzing 500 different open source projects, almost all the critical open source projects, and currently they're using 100,000 machines, 24 hours, 7 days a week, right? So let's take the old numbers, 25,000 machines, and so they are running out of bugs because they've been fuzzing for such a long time. They are deciding to upgrade by 100-fold. Suddenly they have 100 times more machines, which means they have 2.5 million machines, hypothetically. And in 1 month, they find 100 vulnerabilities more. My question now, and you can answer in chat again, how long do you expect it would take to find all of these known vulnerabilities on 250 million machines? So we are scaling again by 100 times more machines. So the answer is intuitive. Like if I have violated your intuition now, here your intuition is right. You cut the 1 month by 100, so it's 1/100th of a month, less than 1 day. If you have 100 times more resources, you find the same bugs So yeah, I have this here. If you have 100 times more resources, you find the same bugs also 100 times faster. Given the same non-deterministic fuzzer, finding the same bugs linearly faster requires linearly more machines. It's very intuitive. So now the next question, and this might not be intuitive. If you have, so you now have 250 million machines, right? How many more undiscovered vulnerabilities do you expect to find in 1 month? So here's maybe 200, not much more. We are going in the right direction. Not much after 4 years, you probably approached the asymptote. Now, I mean, we have 100 times more machines, right? So the answer is, 2 of you said 200 or 100, maybe the same, roughly the same. Richard was saying roughly the same. And the answer is, so that's the correct answer, right? And that's counterintuitive. Given the same non-deterministic fuzzer, finding linearly more new bugs in 1 month or a constant number of months requires exponentially more machines. And in order to visualize this for you, as you increase the number of machines exponentially, you only find linearly more new bugs. So we talked about the software testing problem. And we have scratched out a few things and tried to amend due to certain challenges that we face in program software testing. So currently the problem is generate at least 1 test input for as many coverage elements in the program as possible to achieve the goal of finding all the bugs in the program. And we're also assuming the perfect test oracle. And we are assuming that there's a correlation between coverage increase and bug finding increase. I've talked about different components of software testing, including system testing and unit testing. I've talked about different ways of generating test inputs. I've talked about different ways of detecting bugs, so different test oracles. I've talked about very fundamental challenges in software testing that we still don't know how to address, or just starting to understand how we can address them. And I've talked about other limitations, particularly concerning efficiency and scalability. So if any of this, if you find really interesting, and then I would definitely encourage you to attend different workshops and talks here at ECOOP and ISTA. There's a nice book called The Fuzzing Book. Andreas is the main author of this book, which you should definitely read and check out and try, because it has a lot of good examples. There's also a perspective article written on the challenges and reflections in automatic testing called fuzzing. And as Andreas mentioned, I'm starting a new group in Germany. So you're definitely welcome to send me a message and catch up, talk about opportunities for PhD or postdoc. Thank you so much for having me. If you have any questions, you're welcome to ask them now.